Particle Lenia, a step forward in our understanding of cognitive subjects and individuality, reflects the adaptability and resilience of natural systems. It demonstrates mass conservative evolution, showcasing the dynamic interplay of rules and their results. As we delve deeper, we'll uncover some parallels between these digital realms of cellular automata and real-world computational physics, offering a new perspective on differential equations and physics simulations in general. Now let's explore the classic Conway's game of life, a cellular automaton that simulates the birth, survival, and death of cells on a grid, mirroring the dynamics of population growth and interaction. The rules are elegantly simple. Each cell on the grid has two states, alive or dead, binary. The fate of each cell in the next generation depends on its neighbors. Here are the rules. A live cell with fewer than 2 neighbors that are alive dies. This is sort of an underpopulation representation. A live cell with 2 or 3 live neighbors lives on. This is a society which is healthy and can thrive. If there's a live cell with more than 3 live neighbors, it dies, and that represents overpopulation. If there's a dead cell with exactly 3 live neighbors, it becomes alive. You might imagine this as sort of a 3-member reproductive cycle. These rules are obviously reminiscent of population dynamics. Underpopulation and overpopulation lead to death, and balancing the number of neighbors ensures survival. The concept of reproduction is elegantly captured as dead cells springing back to life in the right conditions. Even with rules these simple, some very complex patterns can emerge. There are stable formations, such as oscillators and even self-replicating structures that can arise, mimicking the unpredictability and diversity of life. Even though this model is abstract, it does provide insights into the real-world population dynamics and the delicate balance needed for sustainable growth. Now suppose we took the binary game of life and we expanded it to a continuous space in which rather than having a discrete alive or dead state, we have some sort of population densities. The integral, or the sum over the population densities in an area, determines the life or death, or rather, the change in population density of each cell. And when we expand to this continuous case, the game is now called Lenia. You'll find that the same sorts of structures as in the previous game of life can arise, oscillators and replicators, propagators, but now they have an almost fluid nature. We could think of this shift in our representation something like the transition in mathematics from discrete Riemann sums to continuous integrals and macroscopic densities. Again, we see that in this highly simplified computational world, even with only a few simple rules, we can end up with behaviors that are really quite similar to things that we see in real life. In fact, in Lenia, it is even possible to create structures which have self-healing functionality, not unlike how your cells can die individually, but your body as a whole does not die, that areas can repair, and your structure as a macroscopic organism still moves on as a whole. Now we're ready to enter the world of particle Lenia, which is one of the best takes on the game of life I've ever encountered. It is inspired by Lenia in the sense that it uses a continuous value space, but one of the researchers at Google had the idea to use the Lennard-Jones potential instead of the traditional rules of determining how the population would change. If you think about it, the Lennard-Jones potential is very much akin to Conway's game of life. For instance, if the radius between 2 life forms were 0, if we set radius equal to 0 in the Lennard-Jones potential, it would blow up off to infinity, which indicates that it's highly energetically unfavorable, you could say, for too many beings to be living closely together. Now let's turn our attention to the center behavior of the Lennard-Jones potential. Here, where the valley is, we would normally represent the equilibrium position of ions in a lattice, for instance. when being used as a representation of Conway's game of life, it represents the idea that it is most favorable for beings to be a certain distance apart, that they need a little bit of space to thrive, but that they need to be fairly close together. And so this imposes a certain length scale on the structures within particle lineae. Then, as we move out, as r goes off to infinity, we rise back up to a plateau, which is not as unfavorable as being extremely population dense, but which is not as favorable as being somewhat close to other particles. It is very clear that these are, in essence, when spoken aloud, the same rules as Conway's game of life. The only difference here is the representation theory behind how we implement it. And as such, the researchers at Google went about doing so. The emergent phenomena that come out of particle lineae are remarkable and a very good demonstration of the idea of metastable states, which is something that was very confusing to me when I first encountered it. Steady states, too, were a strange idea to me, the idea that something in constant oscillation could in and of itself be steady. However, this is a very important concept in the universe. There are, for instance, discrete time crystals, in which where time symmetry in matter is broken, without even introducing external energy, there is a constant phase transition which is occurring just under the influence of the rules of the universe. Sometimes we think of things as being vacuum energy, but I think maybe it's less good to think of it as an energy so much as just part of the rules, in the same way that metastable states and particle lineae form simply out of the rules. Another example of metastable states we find in our higher level physics is within quantum chromodynamics, in which where we have color cycles. Despite the fact that the atoms on our scale, that the protons and neutrons are relatively stable things to us, just little specks of dust, we know that on the inside it is an incredibly dynamic environment, and despite the fact it is changing continuously in this metastable fashion, the structure as a whole, the structure from our perspective of interaction, stays essentially the same. That's something which is really hard to wrap your head around in a purely mathematical sense, I think, but it's really rather clear when you watch it in the form of a worm, for instance, in particle lineae. It can have a number of different combinations of the chambers, opened or closed, but they open and close in a fixed order based on the sensitive initial conditions. In this same way, every proton is a proton because of its sensitivity to its initial conditions. It ended up there because a lot of things in the universe's history moved it towards being there. But now that it's been set up as a proton, despite its dynamic, screaming environment on the inside, for a very, very long time, protons are likely to stay as protons. To close, I'd like to discuss some fun applications of cellular automata that I've explored, starting with a very simple one. Imagine the rules that two objects pull each other together, and the closer they are, the stronger they pull. It is a fairly simple rule, and it's one which we see in many places in physics. As we see this particular orbital structure unfold, we'll recognize this, however, as being a pretty good simulation of gravity, of the orbital patterns between two bodies of equal masses. Moving on to something a little bit more complicated, I'd like to discuss the idea of differential equations as cellular automata in general. At one point in time, we thought of a particle as a point that moved along some continuous space of coordinates, and we parameterized it with time. But looking deep into quantum chromodynamics, it seems a little bit more accurate to think of matter as disturbances in various overlapping fields that are moving in cohort with each other. And if you think about it, that's awfully similar to the structures that we're seeing in lineae or particle lineae. Every numerical differential equation is essentially a group of neighbors and rules that describe how each neighbor updates based upon the area around it. Even in the continuous case of the purely mathematical differential equations, this is still the same. We often describe the functions not as the curve along which we expect something to follow, but rather we describe the rules at every point regarding its neighbors and the passage of time. I've programmed a number of universes, some with third-order wave equations or stochastic wave equations or non-local wave equations. I find it very comforting that in our era, despite the fact we are stuck with a certain set of physics that we're born with, we are not limited to them. Within our computational universes, we can explore emergent phenomena for any number of rules. But I think it's important to remember that any rules that we can conceive of are products of fundamental symmetries of the universe, because ideas are real objects in the universe. Sometimes when we explore these computational universes, even doing something outright silly, we may find something new about real physics, or at the very least, some new intuition.